Hello, my name is Tony Lentz with FCT Assembly, and this is Fill the Void 4, Elimination of Inter-Via Voiding. This is part 4 in a series of papers we've presented on methods of reducing voiding in solder joints. This particular paper deals with via and pad designs on QFN thermal pads specifically. This is commonly used as a method of taking heat out of QFNs and other types of bottom terminated components. So via holes and pads are well known to influence or increase voiding in solder joints, although the results I got in this presentation would disagree with that particular theory. First, we'll go over a brief introduction on the types of voiding that we're looking at. Then we'll talk a little bit about the factors that influence voiding that were studied in this paper. We'll go into some details on the methodology that we used and the parameters that we used to run our tests. Then we'll cover the voiding results with lots of images of representative voiding for each type of variable that we studied. Then we'll make some recommendations to fill the void based on what we saw in this work. Then I have an acknowledgement for one of my counterparts who assisted with this study. And at the end, if you have any questions, please email me using the contact information on the last slide in this presentation. So voiding is a common problem for QFN thermal pads, especially with via holes in the pads. So we designed a test board with pads that look like this. This is a 10mm QFN body with a 7x7 grid of via holes in the pad. And this grid of holes was designed based on the component manufacturer's recommendations. This type of design produced voiding that looked like this. You can see some voids sort of in the holes themselves where they didn't fill completely with solder. Then you've got a lot of random voiding kind of scattered around in the thermal pad solder joint. Then on the right, this is a colorized image of the same X-ray image. It makes it a little easier to see the voiding that's going on by colorizing it. So the lighter blue color here, or the aqua color, are the voids, and then the darker blue color is the solid solder joint. Here are the three different via plugging options that we studied in this work. On the left, we have completely open via holes. So we designed this test board to have the same QFN pad layout on the top and bottom surfaces of a double-sided circuit board. And then we had via holes drilled and plated through. So these via holes are plated with copper. And then the entire circuit board was finished with ENIG surface finish. You can see for the larger QFN size, we have a 7x7 grid of via holes. And for the smaller QFN thermal pad, it's a 4x4 grid of via holes. In the center, what we have is a solder mask tenting option. This is commonly done because it's a cost-effective way of capping one side of the vias. So on the bottom side of the circuit board, or the non-solder side, we had this PCB manufacturer cover that with solder mask. So the solder mask does not plug the via holes, but it does tent over some of them. Some of them are actually capped with solder mask. And then on the right is the third option of via plugging. This is a completely plugged via option. And you can see the plugging process and the plugging material that they use has some topography to it. It's not completely flat. Some of these little bumps are raised above the surface of the pad, and some of them are kind of dished in below the surface of the pad. And that's just part of the nature of using a thermally curable plugging material in via holes. Here's the two different stencil designs that we used. This is what the printed solder paste looks like. On the left, we are printing just a normal window pane, which is standard for this thermal pad design. And these window panes are printed without regard to the via hole location. And so you can see we've got solder paste being printed directly over the via holes. On the right, we modified that stencil design with the intention of printing around the vias. So you can see all the via holes are open here. Solder paste is not being printed over them. And we did that intentionally by creating this web design with little circles of clearance in the stencil around each via hole. Here is the methodology that we used and the details on the experimental design. Here's an image of the circuit board that we used. This is called a PR test board. It has a VN pad design in it. These via holes are 12 mil diameter drilled vias. They're plated with copper and ENIG, and they're plated down to roughly a 10 mil hole diameter. over those holes. In where some of them are tinted, is this. This is an image of the and they used a non-conductive via fill material to plug the and then plated the final enig finish. Via holes are completely plugged in the left. They both have a matte tin surface finish on them. Stencil design that we used. This particular stencil design is a standard window pane design on both sizes of QFNs. You can see it's a 9 window pane, and these window panes are designed to have a 65% area of coverage over the thermal pad. Here's the modified stencil design where we changed that standard stencil design and we intentionally printed around the via holes. This particular case, the coverage, we could only get it up to about 63.3% area coverage. We were trying to get it to 65 to match the other stencil, but it wasn't possible due to the grid that we put in place here. The web width is about 8 mils, and then the clearance around the via hole is a 5 mil radius clearance around each via hole pad. So the hole size itself was finished to about 10 mils. The clearance in the stencil is about 20 mils total printing around these via holes. The solder paste that we use is a no clean sack type 3 solder paste, which is one of the solder pastes that we used in a lot of our previous work so that we can compare and contrast data sets. The reflow profile is shown on the right. Ramp to peak profile, which we profile. This is pretty QFN size on each circuit board. So there's 8 total QFNs per board. Now we reflowed the boards. We measured void area and we took images of QFN voiding that were representative for each experiment. Then we analyzed the data and generated some statistical analysis of the data sets. Here are the voiding results. So here are images of the first set of voiding results. This is via fill option broken out by QFN size. Quite a bit of voiding here. This is pretty true of all the completely plugged via boards. You've got large voids, you've got a scattering of quite a variety of sizes. Void area is definitely higher than the tinted and open vias, but not quite as high as the completely plugged. Here are images of the voiding that we got with the model around the via holes. So little light blue coloration. Voiding, you got that I'm using here. Our PR is the flat via is the completely open via holes. And what this is now significantly different. If the letter codes are the same, then they are statistically similar data sets. So what you can see here is that the flat PR pad without any via holes gives you a second to largest void size. The plugged vias give the overall largest void size, and then the tented and open via holes give overall smallest void size, and these are significantly different from each other. With the modified STENCIL design on the right, the same is true. The plugged vias give overall larger voiding, than the tented and open via holes give overall smaller voids. So voiding size analysis follows what we saw in the images, where we were seeing much more voiding or higher void area with the plugged vias versus the other types of via options. Here are some images on the back side of the board to show you what's happening with the solder flowing to the bottom side. With the standard STENCIL design, where we're printing directly over the via holes, and the open via holes, you can see a lot of holes were open. You could see daylight through them before printing and reflowing solder paste. And on the right, we have the completely plugged vias. Of course, there's no solder flowing there for the solder to get to the bottom surface. The modified STENCIL design is shown on the right. So here you can see some differences. The modified STENCIL design did limit the amount of solder that flowed down to the bottom of the open via holes. You can see very little solder here. And the same is true for there's very little solder flowing to the bottom surface when you print around the via holes. And I wanted to break this apart and analyze this separate from the via designs, just because I kept seeing an effect where it looked like the larger QFNs had less voiding and smaller voids than the smaller QFNs. So I wanted to analyze the statistics here to see if that was absolutely true. And what I found is that it certainly was true. On the left here we have the largest void size analysis. The QFN 10 gives overall smaller voids than the QFN 7, and these are statistically different results. For void area, the QFN 7 gives overall higher void area than the QFN 10. And again, these letter codes are different, so the statistic analysis shows that that is significant. That's significantly higher void area with a smaller QFN. Now I was trying to reason out why this would be. The mass of the QFNs is quite different. The larger QFN has about double the mass of the smaller QFN. So one theory would be that the larger QFN can actually help to push and squeeze out any gas bubbles that might be in the solder joint, and maybe make better contact with the solder paste to improve wetting or flow behavior of the solder paste to that thermal pad on the bottom surface of the component. That would help reduce void size and void area. That's just one possible theory. I'm sure there's a lot of other things that might be going on here that I don't have any details or data to discuss, so I won't postulate any wild ideas any further. Here are recommendations to fill the void based on what we saw in this particular study. First of all, void size can be reduced using via holes and QFN thermal pads. This is completely the opposite result of what I was expecting. I expected that the via hole in pad would generate higher voiding and more voids, and that's not what I saw. I saw that the completely plugged vias definitely had higher and larger voids. Now that might be due to some localized heat sinking that's going to be going on with a completely plugged via. The completely plugged vias have a much better ability at wicking heat away because there's some thermal mass to them that's greater than an open via hole. And so it's possible that the reflow profile is a little bit different right over each plugged via hole location. Maybe it's a little cooler. And because the profiles change just in that little region, it's possible that gas bubbles are being generated around those plugged vias a little later in the profile and then could be coming trapped as the solder freezes. That's just one possible theory. I wish I had microscopic cameras to see what was going on during reflow in these solder joints, and then maybe I could give a better reason for why this is happening. Unfortunately, I don't have that type of equipment in my laboratory. We did see that modifications of the STENCIL design limited the amount of solder flow through the via holes, but it did not affect void size or overall void area. Modifying the STENCIL design didn't seem to change the voiding behavior itself. Although limiting the amount of solder flow to the backside of the circuit board is definitely desirable. We wouldn't want solder flowing through open via holes down to a bottom pad. And then we also saw that using larger QFNs reduced overall voiding. It reduced void size and void area. So if you have the ability to change the QFN that you're using a larger component might help. And that might be true of other types of bottom terminated components. That's something that we could study in future work. One thing that we know for sure is that via hole and QFN thermal pads certainly influence voiding. So in terms of future work, we continue to work on ways of reducing voiding in solder joints, and we will be happy to present that information at future technical conferences. I would like to acknowledge my counterpart Greg Smith with Blue Ring Stencils, who designed and supplied the stencils that we used in this work. Thank you for your time and attention and listening to this presentation. If you have any questions, please reach out to us. You can contact me via email, or you can reach us on our website through our web form or calling us by telephone, however you prefer to do it. We would love to hear from you. Thank you and have a great day.